looked at the definition of a commutative group and also a group, which I have not written down here, but I assume that it's very clear that except for the property number 3 here, which is commutativity, all other properties are satisfied, which is the case in, for example, 3 here. All other examples that we looked at yesterday were commutative groups. Now, in this course, we will primarily focus on commutative groups. There will be occasions when I talk about non-commutative groups or general groups, but mostly we will stick to commutative groups, and that's why I have given the definition of commutative group first. Now, of the 2 examples given yesterday, the first one, which is numbers under addition, is a natural obvious examples of a commutative group. That's how we actually derive the properties of a group as well. But if you look at the fourth one, that's already a bit of a surprise, because it's a group of non-zero numbers under multiplication. It's a commutative group because it satisfies all the properties as we had listed them, but the nature of these 2 operations, addition and multiplication, seems very different. And what we have learned from this abstraction is that while on the face of it, these 2 operations look very different, at a certain abstraction level they are the same. And that's the first important learning we have. And already we are seeing the benefits of abstraction. Now we can actually look at both the operation with the same perspective. Okay, so now that we have defined what a group is, there are 2 directions in which we can proceed. The first one is to continue with our abstraction process, which we started with numbers. Right now we are only at halfway stage, because we have just abstracted out the addition operation property or multiplication operation property as well, maybe. But we have not talked about the entire arithmetic. Remember, these numbers admit both addition and multiplication operation, and we don't yet have a definition of a structure in an abstract way which admits 2 operations, addition and multiplication. The other direction would be to just start focusing on groups and see what are the properties of groups. So what I am going to do is, very quickly I will do the full arithmetic abstraction. Then we will shift our attention to groups, and then later on, once we are done with groups, we will move on to the full arithmetic abstraction. Let me first give some, at least abstract it out and give a definition. So for a full arithmetic to happen over a set of numbers, we have to define 2 operations: addition, multiplication, and then of course addition comes in conjunction with subtraction, and similarly multiplication comes in conjunction with division. Now with division, we have already observed in certain set of numbers division is not possible. For example, integers, division is not possible. So with division, there is always this bit of let's say carefulness that is needed to distinguish these cases where division is possible and where division is not possible. So let's first define a setup or a structure which may or may not have division, which is a more general types of numbers which span everything. So what are the other properties that we need? Just like we identified for groups, we had these 5 properties for addition. Surely when we are talking of 2 operations, addition should still retain those properties. And now let's define a structure So, I will have two operations, addition and multiplication, such that first A is a commutative group under addition. That is again borrowing the property from numbers. Addition is a commutative. Now, let us bring in multiplication. We should not say that A is commutative group under multiplication, although there are certain types of number where it is true, but we do not want to say that yet. So, what are the, let us look at integers and what are the properties that integers satisfy, multiplication satisfy for integers. If you just go back to the group properties, we will see that A is closed under multiplication, then the associativity, associativity holds for multiplication. Multiplication satisfies commutativity property, A times B is B times A. Then there is the identity also present. Again, I am simply picking up properties from the definition of groups. The identity is 1 for the multiplication. The only one that I have left out is the inverse, because the inverse again may or may not exist. That's a big saying that again and again. So, let us leave out inverse because we want to capture numbers in general. Is there anything else? Yes, because there is the multiplication and addition interact in a certain way, and that we have not yet captured. And that is captured by a very simple property called distributivity, which is that for any 3 elements A, B, C in A times B plus C is same as A times B plus A times C. That is again very obvious property that multiplication and addition satisfy, and that we want to carry over or abstract out. This is called distributivity property. And that is it. That is the structure with two operations which mimics the arithmetic operations over numbers. So, a structure like this, which is now addition and multiplication, name for this, it is called a commutative ring. Again, commutative prefix is because multiplication satisfies commutativity property. By definition, in a ring, addition is always commutative. It is only multiplication that may or may not be commutative, and if it is commutative, the ring is called a commutative ring. If it is not commutative, it is just called a ring. And just like with groups, we will almost always be concerned with commutative rings in this course. So that is why we are defining it first. Any questions on this? Well, in certain, you are right in that in certain more general definitions of a ring, the multiplicative identity may not exist, but we will not define it in that general sense. So, we will always assume that multiplicative identity, that is 1, exists. Okay. So, this abstraction tells us that set of integers under addition and multiplicative operations are a commutative ring. So is the set of rational numbers, real numbers, complex numbers, etc. They all are commutative rings. Some of them even admit division. So that's the next step or next definition that I want to define. That is the third definition, that in case this structure, which is a commutative ring, also has inverse for every non-zero element, inverse, that is under multiplication, which is another way of saying is that for every A in this collection, which is non-zero, there exists a B such that A times B is 1. This defines division, because 1 by A is B. In that case, the structure is called a field. Examples of this: well, set of integers under addition, multiplication is a ring, is a commutative ring. If you look at rational numbers under addition, multiplication, that is a field. So are real numbers under addition, multiplication, and complex numbers under addition, multiplication. Going back to yesterday's example, set of n cross n matrices under matrix addition and matrix multiplication. What structure is that? We saw that under addition it is a commutative group. How about multiplication? Does it, let us see, closure property, is it there? Associativity, there we have seen that A times B times C is AB, or whichever way you multiply you get the same result. Commutativity, not necessarily true. Identity, yes, the identity matrix is the identity element. Then finally, for the field, the inverse, not necessarily true. A matrix may or may not be invertible. So, this is a ring, not a commutative ring. It is a ring. By the way, why have I not included inverse of 0? I said that for every non-zero element A, when I defining a field, every non-zero element A, it has an inverse. What about 0? Well, for numbers, certainly 0 doesn't have an inverse. There is 1 by 0 is infinity, which is not a number. But that doesn't rule out a general, and we have abstracted it out. So, could it be possible that there exists a set of different set of numbers with the arithmetic on them, such that there is a multiplicative inverse of 0?
What will be able to prove that 0 into A is 0? If that is true, then
0 into A is 0. Okay, that's another interesting observation. Is it true? It's true for numbers, but is it true for a, let's say, a field or a commutative ring? Okay, so let's prove a theorem, our first theorem. We can prove both the properties. Let's try to prove the first one. A into 0 is 0 for every A. How do you prove that? This is a good exercise, because while we can try to take the intuition from numbers, we cannot be working on numbers here. We are just working with symbols with a certain properties. So, we have to keep that in mind. So, how do we prove A times 0 is 0? It's very simple. Let's say A times 0 is B. Okay. Then B is A times 0, which is A times 0 is, by definition of 0, and in negation, take any element, let's say C in or YC, take A itself, then 0 is A minus A. So, I can write 0 as A minus A. Now, use distributivity property of multiplication over addition. See, although I have written it here A minus A, it's really A plus minus of A. So, I can distribute this multiplication. So, that is A times A plus A times minus A. Now, what is A times minus A? Is it minus of A times A? For numbers, of course, yes, but these are not numbers of the kind that we are familiar with. So, we will have to prove this. Okay, can I write it this way? Is minus A minus 1 times A? It should be, but is it? Or you see it's obvious. Is it obvious? Nothing is obvious. We have to prove, it's like learning arithmetic in class 1. You have to redo that learning, because although these structures are similar to numbers, they are not really numbers of the kind we know of. So, therefore I have to open another front here, that is look at minus 1 times A, and I want to prove that it is minus A. So, add A to it. This is minus 1 times A plus 1 times A. That is because 1 is the identity of multiplication. Now, by distributivity property, this is minus A minus 1 plus 1 times A, and that is 0 times A. And what is 0 times A? That is what we are trying to prove. So, we have cycled back to that original question. So, we are still stuck. We can prove one of them, we will prove the other one, but this way we can't prove any of them, because one property is dependent on the other property. So, we need to come up with an alternative way of proving this. Alright, so let me tell you what, this is an excellent assignment problem. So, I will, instead of proving it here, which when I give the proof and you just write it down, it will be very useful if you prove it yourself. Just play around with these symbols. You have all the properties at your disposal and try to prove this. Okay? So, prove the rest of the theorem. But we will take the statement of the theorem as given to us, as proven that is, and which means that the A times 0 is 0. So, which means that once you prove 1, 2 is pretty straightforward. Second property, that A times 0 cannot be 1. So, 0 has no multiplicative inverse in the collection, which is why in the definition I have to explicitly write that multiplicative inverse exists only for non-zero elements. Okay, so that's commutative ring and field. We will now not talk about rings and fields until some more time. We will pick this thread up once we are finished with groups, because in order to understand rings and fields, we first have to understand groups, because under addition there is a group all sitting in both of them. So, let us try to understand groups first and their properties. Now, let us, for the study of groups, let us try to, or let us adopt certain notation. So, the structure that we will represent as groups, typically we use the capital G to denote the set of elements or objects, and the group operation, which earlier when I gave the definition I used plus. Now, I am going to use dot as the representative group operation. This has a certain logic to this, because generally the addition operation in whatever context we use it is commutative. But multiplication operation, depending on context, may be commutative, may not be commutative. We've seen examples of that. That composition, which is also denoted as multiplication or matrix multiplication, that's not commutative. So, when we talk of a general group which could be commutative or not commutative, it's better to use a multiplication symbol as its operation. And that's why we write groups multiplicatively more often than we write them additively. So, let G dot be a general group. Now, when we want to study a structure, what exactly, or its properties, what exactly should we be looking for? One very important aspect is the structure of the group. How really does it look like? Once, if you understand the structure of the group, then we can derive the properties of the group a lot more easily. But what does it mean to say the structure of a group? Well, structure is like, in a sense, certain specific properties, like structure of integers, you can visualize them as lying on a number line, equally spaced, and there is each next point can be achieved by adding 1 to the previous point. So that's basically denotes the structure of that particular group. So in general, if G is a group, we would like to understand what is the structure. And one very important aspect of that is to see if within the group G, if there are more groups. And that's question is important enough to have its own definition. So let's define that. Take any subset H of G. It's a subset of elements of G, and we call this subset a subgroup of G if H under the same dot operation is a group. Examples. It's always good to have a certain connection of these abstract entities with the actual ones. So for groups, it's good to keep two example groups in mind. One is numbers under addition, the other is numbers under multiplication. Okay, they both are groups, but both have a very different structure, as we will see later on. Okay, so examples. Okay, in integers over addition, are there subgroups in that? Even integers, yes, excellent, yes. 2z, which is set of is a subgroup. How about numbers under, let's say, rational numbers under multiplication? You see a subgroup there? positive? Positive rationals. That's a subgroup under multiplication. That's right. So the subgroup of Q star. So Q star is defined as a set of non-zero rational numbers. So we do have subgroups, and in fact these are not the only subgroups that you can find in these groups. You can have 3Z is also a subgroup, 4Z is also a subgroup under addition. For group rational numbers under multiplication, you can again create a lot of other subgroups. Again, let's see the examples. Being for, let's say this set 2 to the n. N is an integer. Is a subgroup of rational numbers under multiplication. Do you see this? It's straightforward. Right? You can multiply any of these two elements, its closure and all other properties are also satisfied. So, subgroups of a group tell us a lot about the structure of that group. In fact, there is one very important way of writing a group in terms of its subgroups. Because just imagine the following. You have a group, you identify a collection of subgroups of that group. Each subgroup is in a sense smaller than the group itself. And you keep identifying further subgroups of that, right, until it's possible that this process can continue forever. It is also possible that this process stops after some time. In either case, you have a very nice hierarchy of subgroups of that group, and that structure of that hierarchy will tell us the structure of the group itself. So, one very nice way that this hierarchy is at times defined is when I can write a group as a direct product of two subgroups. Let me define that. So, let us G be a group and H1, H2 be subgroups of G. And now I am going to define what is called the direct product of H1 and H2, which is written as H1 cross H2. It is simply a pair of elements A, B, where A belongs to H1 and B belongs to H2. In fact, instead of calling it observation, this is really a lemma. H1 cross H2 is a group under component-wise multiplication. You understand what component-wise multiplication is? The elements of H1, H2 are pairs. So, with given two such pairs, you multiply them component-wise. And there is a natural way of doing it because first component belongs to H1, second component belongs to H2, and there is a multiplication operation defined both on H1 and H2. The nice thing or interesting thing is that this is a group. Why? We can quickly run through all the properties. Closure, trivially there. Associativity, trivially there. Because component-wise, it's basically we are borrowing properties of H1 and H2. Closure, associativity, well, and if H1, H2 are commutative, then so is this commutative. If not, then no. Then identity, what is identity? Identity is, the pair 1, 1. The identity of H1, identity of H2, which both happen to be the same because they are both subgroups of G. Inverse, again borrowed from H1, H2, everything is just borrowed from H1, H2, and clearly therefore this is a group. This in itself doesn't tell us something very interesting, just we have seen a way of creating a new group from given two groups using this direct product. What is interesting is the following, that is, if G can be written as H1 cross H2. By that what I mean is every element of G can be uniquely identified with an element of H1 cross H2, such that when we do the operation on elements of G, that is exactly the same operation that we do on H1 cross H2. We already defined a group operation on H1 cross H2. That operation and the operation of elements on G, they are identical. You see what I am trying to say? Okay, now then let's do an example. Let's say, consider Q star under multiplication. Okay. And we define H1 to be 2 to the n in Z, and H2 to be all rational numbers in Q star by B, which is a rational number A, B in Z, and 2 does not divide A or B. Of course, I have to say A, B not 0 also. So H2 is all those non-zero rational numbers such that 2 doesn't occur in the numerator or denominator as a multiplier. So that is both A and B are odd numbers. That's a simpler way of saying this. Is this a subgroup of Q star under multiplication? Yes or no? If yes, then why? B by A of the same form, odd by odd. Yes.
Identity is
1 by 1 again, same, correct?
Other properties are basically.
Yeah, the only thing is, I think the key thing is the closure. A by B times A prime by B prime. It's just that A prime is odd, so their product is odd. B prime is product is odd, and therefore everything is. takes care of itself. So, this is also a subgroup. What is H1 cross H2? Is the pair collection 2 to the n times A by B, right? Now comes the key point. Look at any element of Q star. I can write it as C1 by C2, where C1, C2 are integers. Now take out the even powers of 2 from C1, powers of 2 from C2. So I can write this as 2 to the maybe m times C1 prime by C2 prime, where C1 prime, C2 prime are odd and m is any integer, positive or negative, whatever the case may be. So this is in one-to-one correspondence with 2 to the m comma C1 prime by C2 prime. See, this view allows us to transform a given element of Q star to the corresponding elements of H1 cross H2 and vice versa. If you are given an element of H1 cross H2, just multiply the two of them and you get an element of Q star. If you get an element of Q star, you do this process of separating out powers of 2 and then that splits as an element of H1 cross H2. So this correspondence I claim is 1-to-1. Do you see that? If you have two numbers C, C prime mapping in the same way to the same, that means their powers of 2 are the same and the odd component are the same, then numbers have to be the same. And similarly, the reverse way, if two elements of H1 cross H2 map to the same product, then since the product have separate powers of 2 and odd parts, again they will both be the same numbers. So it's a very simple correspondence which shows that Q star can be viewed as H1 cross H2. One more thing, the group operation on Q star, we should also ensure that it is same as the group operation on H1 cross H2. Group operation on Q star is the multiplication. When you multiply two numbers of Q star, what happens to the powers of 2 present? You multiply the powers of 2 of the two numbers and the odd parts also you multiply them, which is exactly what the operation on H1 cross H2 is. So this demonstrates a complete correspondence between Q star and H1 cross H2. And that's the situation when we say that a group like Q star can be factored or written as a product of two subgroups. Are you with me so far? Yes? So let's formalize this. This is just an example to motivate this definition which I am going to give now. The key thing is this correspondence. How do we formally state this correspondence between the group and the product H1 cross H2? And that is done through the notion of an isomorphism. In fact, I'll do it in 2 steps. Let G dot and H star be 2 groups. we say that given two groups G and H under their own group operations, a mapping phi taking elements of G to elements of H is a homomorphism if the following property holds, and the property simply says that the mapping phi respects the group operations. Phi of A dot B is a group operation of G. Phi of that element, which you obtain after doing A dot B, is same as phi of A star phi of B. Star is a group operation under H. So it doesn't matter whether we first do the group operation in G and then apply phi, or first apply phi and then do the group operation in H. Okay, so this is also in a way saying that phi preserves the group operation while moving from G to H. And then comes the second definition. In a homomorphism, it is not necessary that the mapping phi is a one-to-one or on-to mapping. Phi is an isomorphism if phi happens to be a one-to-one and on-to mapping from G to H, then it is called an isomorphism. So it's a isomorphism is a very special kind of homomorphism, and it is the isomorphism that we have been talking about earlier when we say that G can be written as H1 cross H2. What I really formally want to say there is that G is isomorphic to H1 cross H2, because two isomorphic groups are essentially the same groups. You can put elements into one correspondence and the group operation is preserved. Whatever is the group operation in one side is the group operation on the other side. Okay. So with this definition, I can now finally say that that's the next definition. I am defining a lot of them. Okay. So this is the notation we will use to represent isomorphism between two groups. We will write an equal to and the tilde on top of equal to sign, and this designates that the two groups are isomorphic to each other. Okay, and this is with respect to the previous product definition, that this H1 cross H2, as we had defined H1, H2 being subgroups. If we can write G as a isomorphism, G as isomorphic to H1 cross H2, then it gives us something very nice, or tells us something very nice about the structure of G, that I can actually factor G as two subgroups. Okay, time to stop today, and then we will continue tomorrow.